All right, hey everyone. This is the recording for chapter 6, lecture 1. So we're gonna do three lectures for chapter 6. So here's the first one. Let me share my screen. So chapter 6 is on gases. So this is the chapter where we study about the ideal gas law. So if you guys have taken like intro chem before, um, it's a little bit of a review. Or you might have heard of the ideal gas law, right? We do go more into depth here, but it's really interesting. It's probably one of my favorite chapters when I was a student. All right, so let's start off with properties of gases, right? What are gases? It's one of the states of matter, right? But let's review that, right? Gases are they don't have a fixed shape or a fixed volume, right? Because the gas particles are so far away from each other, right? So that's really one of the main things that how gas is different than solid or liquid, right? It's the amount of space in between the gas particles. So gases also have a lot of kinetic energy, right? So think of how you get to the gas state. Like, how do you get ice to go to steam, right? You have to melt the ice cube to become water, then you keep adding heat until water vaporizes and becomes a gas. So what you're doing is you're inserting kinetic energy into the particles, right, to get to the gas phase. So gases have a lot of kinetic energy. And that is part of the reason why the particles are so far apart, because they have so much kinetic energy, they just fly away, right, from each other. And what that means is that gases will expand to completely fill their container, right? Regardless how big the container is. Okay. So that is, a characteristic of a gas that no other state of matter has, right? That is very compressible because there's so much space in between. You can also squish a gas into a very small volume, right? Or you can expand it into a very large volume. So gases can take on any volume, right? And this is part of the reason why the gas state of matter is also very complex, right? And that's why we spend a whole chapter. There's whole, field of study on on gases, because it's a lot more complex than say solids or liquids, right? Um, so think when you think of a gas, this is what you should think of: little tiny balls, right, which are individual particles that are moving around very fast, and they're doing so randomly until when? Until they hit each other, which then they will bounce off, or they will hit the container wall, right? And when they hit the container wall, they'll bounce back out as well, right? And they'll just go on their way. So they move in a straight line until they bounce off a container wall or each other. And as they are striking the surface, right, the wall of a container, they are exerting a certain amount of force. Okay? And if you take the ratio of force over area, P, force over area, you get P. So P is pressure. Okay, so gas pressure is measured as the force divided by the area at which the force is exerting its over the surface. Right? So here's an example of pressure, right? You guys know force. So you strike, the harder you strike, the more force it is, right? But pressure is the ratio. So here's how you can think of pressure. What would hurt more? Um, a linebacker that is stepping on you with tennis shoes or with high heels, right? Think of it that way. Well, of course, high heels is going to hurt a lot more because the force is not spread out over the area, right? So you'd rather have the person step on you with tennis shoes rather than high heels, right? So the pressure of a gas then depends on three factors. The number of gas particles in a given volume. So of course, if you have more gas particles, it's going to strike the surface more often, right? More frequently, because you have more gas particles. And so therefore force is going to go up, right? And therefore pressure will go up. Factor number 2, the volume of the container. So let's say that you have a large volume where the gases are. Well, if you have a large volume, that means the gas particles have to travel further to strike the wall. And so therefore they're striking the wall less frequently. And so therefore force goes down, right? And also area, right, is going to go up. So therefore pressure will go down. So a bigger volume will result in a lower pressure, right? But if your gas particles are confined to a small space, right? So now the denominator, right, is smaller, right? Well then pressure is going to go up, right? And plus the gas particles are going to hit the container wall more frequently, okay? So of course, smaller the volume, the higher the pressure, right? And then finally, the average speed of the gas particles. Right? This makes sense, right? If the gas particles are faster, it's going to strike the wall with more force, right? And so therefore pressure is going to go up. But if the average speed of the gas particles are slow, then it's not going to strike the surface as hard. And so you're going to have a lower pressure, right? And what is speed? What can regulate the speed of gas particles? Right? We talked about this, right? Temperature, right? So the hotter it is, the more kinetic energy and the faster the gas particles are going to travel, right? So at hotter temperatures, you're going to have higher pressure, right? Colder temperatures, you're going to have lower pressure, right? So it's quite intuitive. If you just imagine, these gas particles flying around and striking the surface, that's pressure. You can reason out a lot of these things. So that's why I think this chapter is so cool. It's like, it's already intuitive. You kind of can reason these things out already. Okay, so the total pressure exerted by a gas depends on several factors, and that includes concentration of the gas, right? So the higher the concentration of the gas, the greater the pressure. Okay. And so as the volume increases, right, the concentration of the gas molecules will decrease. And therefore, that's why if you increase the volume, the pressure is going to go down. Now, why do we study pressure, particularly like air pressure? Well, it's everywhere around us, and it affects us in so many ways. One way that it affects us is every day, the weather, right? The weather that we experience is due to Earth's atmospheric pressure. And if you ever watch like the Weather Channel, Weather Guy, right, you'll see like this map where there's like L's and H, right? Regions of high pressure or regions of low pressure. Well, anytime you see regions of high pressure on the map, it indicates that you have clear weather in that region, right? When you have low pressure region, that's when it's problematic, okay? So just think about like low pressure means it's gonna kind of suck in, all of the winds and, inclement weather into that region. So low, the L indicates that you have unstable weather in that area. Okay, let's look at these two scenarios, guys. You have two jars, right? You can see that both the jars have the same volume, yes? But the one on the left has a lower pressure than the one on the right. Why is that? Because you have more gas particles in the container on the left than container on the right, right? So you have less particles. So if you have less particles, that means that you don't have as much force, right? You don't have as many particles striking the surface, the inner surface of the jar, okay? Whereas on the right, you have way more particles, so more particles will strike the surface of the jar, and therefore increasing the pressure, right? And you can think of your bicycle tire too, right? Sure, everyone's ridden a bike. You have the wheel, you have the tire, right, which is inflated with air. You know that the more air that you put inside, the stiffer, right, the more pressurized the tire becomes. Why? Because you have more particles that are colliding against the surface of the inner tube, right? All right, where else can you find pressure? Also in your ear. So if you guys have ever flown in an airplane, you've experienced like this popped ear syndrome, right? So why is that? Well, let's think about it. As you ascend in an airplane, right? So the plane takes off, your ears will hurt too. But the reason why, right? Let's see which way is the ear being popped. When you're on the ground, you have, let's say 1 atmosphere of pressure, right? That's about at sea level, 1 atmosphere of pressure. But when you're up in the air, right? As we go up in altitude, you guys know that atmospheric pressure decreases, right? So now what happens is the outside has a less pressure than the inside of your head, right? Because your head was just at the ground. So what happens is the pressure inside your head is wanting to push out this way. So it's pushing your eardrums outwards, and that's why your ears hurt, right? Now let's think about descending. So now after you're in the plane for a while, your head will equilibrate, right? Until it feels normal again. And so now inside your head, you have, an atmospheric pressure that is lower than on the ground. So as the plane descends, again, your ears are going to hurt because as it descends, the outside pressure gets larger, right? It keeps increasing. And so it pushes against your eardrums. And now your eardrums are popped inwards. Okay. So when you descend an airplane, you should chew gum, right? That's what they say. Try to equalize that pressure. Or I like to just like hold my nose and blow, right? That will help my eardrums pop back out and you'll feel better again, right? Okay. So how do we measure pressure? The term is called a barometer. And one of the oldest barometers made of mercury. And the way it works is you take a glass tube and it's open on one end, right? And you evacuate it. So that means suck all the air inside out, with like a vacuum. And then you dip that tube into the dish filled with mercury. And then the mercury is going to get sucked up into the tube, right? But it doesn't get sucked up forever and ever because gravity is working against it, of course, right? So that gravity that's pushing down, okay, is what's preventing the mercury column to go up and up and up, right? And so measuring the height of that mercury column will measure the atmospheric pressure. Very clever, right? So it turns out that at sea level, the mercury column can rise to 760 millimeters. Okay, 760 millimeters. And that's that's an exact number. So when you're dealing with it, don't worry about that number as your sig fig, okay? Just ignore it. So what does that mean? At sea level, the mercury column will rise 760 millimeters. And so that's why we have this unit of millimeter mercury, okay? Because obviously it was done with mercury, right? Now you could do this with any liquid, right? Imagine you did this with water. What do you think? Would the column be higher or lower? It would be higher, okay? Because water is less dense than mercury, right? So the column is actually going to be really tall, something like 3 times the height. No, even more. I believe like 10 times the height. So not very practical, right? You can't store, an instrument that is, taller than a building. And so that's why mercury was used, right? So 760 millimeter is quite practical. It can just fit in the corner of the room. And so that's what we use for a while, right? Now to measure pressure like in the lab, let's say you want to know, how much gas you want to react. Okay. This type of measurement device is called manometer. Okay. So barometer is for measuring pressure outside, external pressure, right? Atmospheric pressure. Manometer is to measure gas samples. Okay. So there are 2 types of manometers. One is closed end, looks like this. Figure A here. Figure B gives you sorry, the one on the right gives you the open end. Okay, so let's look at figure A first. Here's the closed end. So you see that you have this glass tube that is U-shaped, and in it is filled with mercury and it's closed. So when the arms are level, it means you don't have any gas in your flask. Okay. Now, let's say you open the stopcock here and you let some gas in. What's going to happen? It will press on the left mercury arm so that you get this J, right? So this J, the difference in height, tells you how much gas you put in there in terms of millimeter mercury, right? Because this is mercury. So it'll tell you how much pressure, right? Gas pressure you put in there. The figures on the right is with an open end. So in an open end manometer, if you see the mercury level equal to each other, what that means is that your gas sample has the same pressure as atmospheric pressure, right? That's why it's equal in arm here, okay? But let's say you put more gas in the flask, or sorry, you take some gas out, right? Then what that means is you're going to have this inverted J, okay? And that's telling you that the pressure of your gas is less than atmospheric pressure, okay? And then you can measure the difference in height to figure out exactly what is the pressure of your gas, right? Because then you just subtract it from atmospheric pressure, right? Now, when you have this J situation, it must mean that the pressure of your gas is higher than atmospheric pressure. So when you measure the difference in height here, you can add it on to atmospheric pressure, right? Which you'd get from the barometer, and it'll tell you what the pressure of your gas is. All right, let's look at the common units of pressure. You guys seen some of these already. Pascal, kilopascal. So PA or KPA. There's the atmosphere. We use this a lot in chemistry, right? Atmosphere. One atmosphere is 1 ATM. That's short for atmosphere. And 1 ATM is exactly 760 millimeter mercury, right? We saw that earlier as another measurement, right? With the barometer. That's also used in chemistry. We also use the torr, and notice that it's the same amount, torr and millimeter mercury. So 1 millimeter mercury is 1 torr. Very simple, right? Then there's the pounds per square inch, which you guys have heard too, PSI, right? So if you have 14.7 pounds per square inch, we use this in engineering, mainly, right? But chemistry as well. And then the bar. This is actually what they use on TV, right? They talk about bar, meteorology, and in chemistry too. So 1 bar is very close to 1 atmosphere, but slightly different, right? So here it is, right? The summary of all the conversion factors for pressure. So 1 ATM is 760 millimeter mercury. You guys are using that a lot, okay? Then you have 1 torr, 1 millimeter mercury are the same thing. 1 ATM is 14.7 PSI. Here are the ones for the pascals and bar, okay? So you don't need to memorize this, right? It's gonna be on your conversion sheet. Go ahead and verify that, right? And let's do an example problem here. It says a high performance road bicycle tire is inflated to a total pressure of 132 PSI. What is this pressure in millimeter mercury? All right, let's go to the board and do this. 132 PSI. Okay, and it wants us to go to millimeter mercury. So first we need to go to ATM, right? And then to millimeter mercury, right? So if you go back to the previous slide, you'll see that to go from PSI to ATM, we need to use equivalency. 1 ATM is equal to 14.7 PSI, right? And then go to ATM to millimeter mercury. We know that 1 ATM is 760 mercury. So here we go, 132 PSI. Okay, what should go on top? What should go on bottom? Well, we're trying to go to ATM. So 1 ATM is going to go on top. 14.7 PSI is going to go on bottom. And then you want millimeter mercury, so 760 millimeter mercury top. So punch that in, right? You should have 3 sig figs. And you should get 6.82 times 10 to the third millimeter. All right. Let's go back to the slides. Okay. Let's talk about blood pressure. Okay, so all pressure is actually very similar, regardless of the state of matter, right? So we've been talking about air pressure, and this chapter is on air pressure, but even liquid pressure has the same physics, okay, the same sort of um, characteristics, okay, and even the equations sometimes are related. Um, so blood pressure. Is basically measuring the force at which the blood is driving through the arteries, right? And also how hard your heart is beating. So when you go to a doctor, they measure your blood pressure with a sphygmomanometer. That's a really hard word to say. Sphygmomanometer. There we go. Um, and then they give you these numbers, right? So if you look at these numbers, you guys know what systolic and diastolic is? There's always like a range, right? And so systolic is always a higher number than the diastolic. Okay, so what it's actually measuring is right at the time that your heart pumps, that's the highest pressure. That's the systolic pressure. Okay. And then it also measures when your heart relaxes. And that's the diastolic number. So it's a way to figure out how hard is your heart's working to pump blood throughout your body, right? So it's a diagnostic that tells you, um, are you gonna have issues with, you know, like heart, high blood pressure, or are you gonna have heart conditions later on in your life? So normal for systolic is 100 to 119. For diastolic is 60 to 79. Right. So a lot of people are probably in pre-hypertension. I know I'm like right here, because I like to eat too much steak, and I like the really fatty part too, right? But you really want to be in the 100 to 119 here, right? Um, so 120 to 139 is pre-hypertension, and then if you're greater than 160, that's stage 2 hypertension, which is not good, and you probably have to take medications to bring it down, right? Okay, so now that we've kind of just introduced what gases are and what pressure is, right? We are going to go and look at the simple gas law. So basically, how do gases behave? And again, I was saying, right, as far as the state of matter, gases are a lot more complex than, say, solids or liquids, right? Because gases can have multiple volume, right? That's not true for a solid or a liquid, right? If I give you the dimensions for a table, length times width times height, you can figure out what the volume is, right, of that table, and it doesn't change, right? But a gas, it does change, okay? So since the volume can change, um, it's affected by a lot of things, right? Temperature and moles and pressure as well. So these four basic properties of a gas are interrelated. And if you change one of them, the other one will change. So that's why it's so complex. Um, so the simple gas laws, we're just going to look at two of these basic gas properties at a time to see how they relate to each other. And in that way, we can understand gases better, right? Just by looking at two, um, rather than looking at four at a time. So we're going to look first at Boyle's law. Boyle's law has to do with pressure and volume. So Robert Boyle decided to study that relationship. And what he did was he took this J tube and he plugged it on one end, and he started to pour mercury on the other end. So what happens is, as he's pouring the mercury, he sees that this gas bubble right here got smaller and smaller. Okay. So then he was like, oh, that's the relationship. As I pour more mercury, I'm increasing pressure on this gas bubble. And what happens to its volume? It decreases. So as pressure goes up, volume goes down, and vice versa. As pressure goes down, volume goes up, right? We call this an inverse relationship, right? Because as one does one thing, the other one does the opposite, right? So inverse relationship. That's what Boyle found between volume and pressure. Here you can see the graph too, right? Boyle's law, as pressure increases, that's on the x-axis. What happens to volume? Volume decreases. So here's a molecular interpretation of Boyle's law. So we really zoom in to see what's going on the molecular level to explain Boyle's law. Let's see, in the left side, right, you have this gas chamber that has a movable piston. And it's 1 liter right now, and the pressure gauge reads 1 atm. Okay. So now what happens when we put more pressure on this piston? Well, what happens to the volume? It decreases, right? So when we increase the pressure to 2 atmosphere, the volume actually got cut in half. Okay. So not only is it a inverse relationship, right? It scales as well. Okay. But how can we explain that on the molecular level? Well, because the volume went down, the gas particles now are closer to the walls. And so they hit the container wall more often. And remember what pressure is? Force over area. So the particles hitting the wall more frequently is what gives rise to an increase in pressure, right? Because your force goes up, right? Okay, so let me go to the board for this one. We can derive what I call the two-condition equation or Boyle's law. So now in Boyle's law, we were studying what? Pressure and volume, and we were keeping moles and temperature constant. Okay, so we said as pressure goes up, volume goes down. And as pressure goes down, volume goes up. This is what we call an inverse relationship. Okay. And to derive the two-condition equation, we can say then volume is inversely related to pressure. Okay, so this little fish symbol just means proportional. Okay, so volume is inversely related to pressure, right? That's why pressure is at the bottom. Okay, and now I can just do algebra, right? If I multiply by P to both sides, I will get PV is proportional to 1. Okay, you guys see that? Everyone's following, right? All I'm doing is multiplying by P on each side. And if I want this to be an equation in math, what I would have to do is introduce a constant. So that P times V, and I'm changing this proportional sign to an equal sign because I want an equation, right? And I have to introduce constant C. All right. So pressure times volume is equal to a constant. Let's introduce a second condition. P2 times V2 should also be equal to a constant. Okay. So now we can equate those to each other. So P1 V1 is equal to P2 V2. This is what I call the two-condition equation. So you can answer questions like this. If I have a gas at a certain pressure and at a certain volume, now I change the pressure. What is my new volume, right? So it allows me to answer those types of questions, right? It's a two-condition equation. That's why I call it that, right? So you have condition 1 and condition 2. Okay. Let's go back to the slide. And we'll do this example problem using that two-condition equation that we just derived, right? A woman has an initial lung volume of 2.75 liters, which is filled with air at an atmospheric pressure of 1.02 atm. If she increases her lung volume to 3.25 liters without inhaling any additional air, what is the pressure in her lungs? Okay, so remember, we had P1, V1, is equal to P2, V2, right? So it doesn't matter which one you call 1 and 2, as long as you keep them together. So a woman has an initial lung volume of 2.75 liters. Let's call that V1, which is filled with air at an atmospheric pressure of 1.02 atm. So let's call that P1. If she increases her lung volume to 3.25 liters. Okay, so it's giving me a new volume. So let's call that V2. What is the pressure in her lungs? So it wants me to figure out the new pressure, right? So you see what I mean? It's a two-condition problem. How can you tell it's a two-condition problem? Well, it's giving you two things, two conditions, right? A before and an after. Okay. So now we're asked to solve for P2. Just algebra it, right? Which means get P2 by itself. How do we get P2 by itself? We need to get V2 to the other side, so we have to divide by V2, right? Dividing by V2 to both sides, right? And so then what do we get? V2 cancels here, so P2 is equal to P1, V1 over V2. And then all we need to do is plug it in, right? P1 is 1.02 atm. And what's V1? 2.75 liters. And we divide by 3.25. So liter will cancel, right? And we should get 1.02. Sorry, 0.863. 0.863 atm. 3 sig figs, right? All right. Okay, so you see, you will always use this equation, right, when you're faced with a two condition problem. Okay, and again, how can you tell? Well, it's like before and after, right? It gives you two things to relate, volume and pressure, and it, it says, oh, here's the original condition, and now I'm changing it, right? All right. So where does Boyle's law apply? Actually, in a lot of places, but one of the very important one is when you're diving. So I don't know if you guys have any experience in diving. It's really cool though, so you should. But when you do go diving, you have to be careful, right? Because for every 10 meters of depth that you go down, you will experience one additional atmospheric pressure. Due to what? Due to all of the weight that is pushing on you from the bottom, from the side, and also from the top, right? I mean, you've seen it, right? You've experienced it when you go even into a swimming pool. When you're under the water, you feel a lot of pressure on you. Okay, so an additional 1 atmosphere every 10 meters. So if you dive to 20 meters depth, you experience a total of 3 atmosphere of pressure. Right. So what that means is when you want to ascend, right? If you're at 20 meters depth and you want to ascend, you need to do that slowly, okay? Because at 3 meters depth, you have the tank is delivering 3 atmosphere of oxygen into your lungs. So your lung is equilibrated, right? 2, 3 atmosphere at this point. So now as you go up, of course, the pressure is going to decrease. So what does that mean? The outside pressure is going to be lower than the pressure in your lung. So your lungs will then try to expand, right? Okay, because as pressure goes down, what happens? Volume goes up. Okay. And so if you ascend too quickly, basically your lungs will explode, right? And so they always teach you you need to go up a few meters and then wait at that depth for your tank to re-equilibrate to the same pressure as the pressure on the outside. Okay. So you do like little steps of ascension so that your lungs don't explode. Right? Also, they always tell you, right? Always exhale when you're rising. Because if you exhale when you're rising, then inside, there's not a lot of air in your lungs to expand, right? So it helps alleviate that issue. Um, Also, I don't know if you guys are probably too young by now to get this reference of the Flintstones. But in this cartoon, you have this guy trying to go snorkeling, basically going diving, right? With this reed. Um, so it's open up here, right? So he's trying to breathe through this really long tube so that he can go like deep sea diving and see fish. Now, what's the problem though with that? Why wouldn't that work? Okay. So the reason is when he's at this depth, right? He's having like what, 2 atmosphere of pressure pressing against his chest, and he's supposed to suck air. Okay, that's like trying to breathe when like a 300-pound person is sitting on your chest. How are you going to actually inhale enough air to keep you alive, right? And so that's why this could never work. Okay, and that's why when we go deep sea diving, we need to use a tank in order for us to be able to adjust to that pressure, right? To get air into our lungs at that pressure. Now the picture on the right's interesting too. It's a nice thought experiment. So let's say that you have a really long pole, and it's hollow, right? It's open, and then at the ends you have balloons tied to it. And now you can move this pole up and down. So let's think about what would happen if you move this pole, this whole system down. So you move this down, the pressure is going to increase on the bottom balloon, right? Which will squeeze it, and it'll get smaller, but the air will travel up, and this balloon will get larger, right? And then what happens as you pull the whole assembly up? Well, then you have a decrease in pressure here of this balloon, right? So the volume is going to do what? Expand, right? Whereas this is going to decrease. So pretty interesting, right? So that's Boyle's law for you. Let's move on to Charles' law. Now, Charles studied the relationship between volume and temperature. And so what has to stay the same? Moles and pressure, okay? So he wanted to know, okay, what happens to volume when you change temperature? And this is quite intuitive. You guys can actually imagine this, right? If you increase the temperature, what you're doing is you're increasing the kinetic energy of the gas particles inside. And so then the gas particles travel faster and they hit the container wall harder. And if the container can move, which direction is going to move? Outwards, right? Because there's going to be more force hitting on the wall, and so the volume will increase. So as the temperature increase, the volume increases, right? Now let's go the other way around. You drop the temperature, so it gets cold. When it gets cold, the gas particles, they don't move as fast, right? And so they hit the container wall with less force, okay? But you want to keep the pressure the same, right? Remember, pressure has to stay the same. So how does pressure stay the same? Well, then the volume has to go down, okay? So let's go to the board and we're going to derive Charles' law. The two condition equation for Charles' law. Right? So Charles' law is going to measure volume and temperature while moles and pressure stay constant. So as temperature goes up, volume goes up. As temperature goes down, volume goes down. So we call this a direct relationship, right? Because one goes up, the other one also goes up, right? Direct relationship as opposed to Boyle's law, which was the inverse relationship, right? Okay, so then when we derive this, we can say volume is directly related to temperature, right? Direct relationship. So they're both in the numerator, okay? But let's bring T to the other side. So now we have V over T is proportional to what, right? And remember, we want to make this into an equation. So we can say V over T is equal to a constant, right? So that means V1 over T1 is equal to a constant. And V2 over T2 has to also equal to a constant. And so we can equate these, right? And it'll be V1 over T1 is equal to V2 over T2. Okay. So this equation allows us to solve problems like, all right, I have a gas that is this volume at this temperature. Now I'm going to change the temperature to this. What is the new volume, right? Or we can even say, now I'm changing the volume to this. What must be the temperature of the gas, right? So you can ask, you have 4 variables, you'll know 3 and you're solving for the 4th, right? Okay, so let's go and do that with this example problem. Oh, before we do that, let's look at this really cool chart. So we have X on the X-axis, we have temperature. On the Y-axis, we have volume, right? So you see these 3 lines. It's linear, right? As temperature goes down, volume goes down. Okay, Charles' law. But these 3 lines are just starting with different numbers of moles of gas, right? And so that's why their slopes are different. But they have the same behavior, right? Temperature goes down, volume goes down. And they all converge at this point. This point is called absolute zero. So what we're saying is if the temperature becomes 0 Kelvin, then you have a 0 volume. Okay. So what does that mean? 0 volume. When do things become 0 volume? Or what happens when things become 0 volume? It means they cease to exist, right? And so this point right here is purely theoretical right now. We cannot reach 0 Kelvin. Okay. We know that technically there is a 0 Kelvin, but we can never reach it because if we do, every single piece of matter will cease to exist, right? So that's very interesting. So of course, scientists have done this, right? They tried, because anytime that you say, oh, you can't reach absolute zero, they'll be like, somebody was like, let me try, right? And so they did. Closest they have gotten to absolute zero is 1.7 Kelvin. And that's if you use liquid helium to cool things, and vacuum and all that, you can get down to 1.7 Kelvin, okay? And even though that seems like really close to zero, it is infinitely far away, okay? Because each minute little temperature change from that point is very, very energy consuming, right? It's very hard to do. Okay, so let's look at this picture here, right? These 2 scenarios, a balloon that's in ice water versus a balloon in boiling water. You can actually do this at home, right? So that you can just see Charles' law at work, okay? So in ice water, the balloon is tiny, okay? It's very small. Then you take it out of the ice water, you put it in boiling water, and it just grows like an alien, okay? Like a little alien baby. Kind of creepy, right? But actually really cool looking too. So if you have ice water, in ice water, the particles are gonna not be moving very fast, right? So what does that mean? The particles will hit the container wall, right? The balloon wall, at less force. And so therefore, pressure initially decreases. But remember, the pressure has to stay the same in Charles' law. So if pressure initially decreases, how can you make it stay the same? By decreasing the volume. So the volume decreases instead, right? To keep the pressure the same. Okay. Now, in boiling water, right? The way to explain that, same way. Think about kinetic energy of the particles. They're higher. So now they're hitting the container wall with more force, which initially increases pressure. But remember, pressure needs to stay constant. So what changes instead? The volume. The volume will go up so that you know uptick in pressure can go back down and stay constant. Okay. So that's what's happening on the molecular view, right? Okay. And another example of Charles' law is a hot air balloon. Okay. And this is really interesting to explain here. So you know why a hot air balloon floats? It's actually Charles' law. So let's think about this. How is that? Temperature goes up, volume goes up. Okay. Now, why do things float? Because of less dense, right? Whatever is less dense floats. Okay. And then what's density again? Mass over volume. So as temperature increases, right, volume increases. And since volume's at the bottom, right, mass over volume, density decreases. So the density in the air, inside the balloon, right, of the air inside the balloon is going to be lower than the density on the outside. And so that's why the hot air balloon floats, right? And people have been saying that for ages, right? Oh, hot air rises, hot air rises. But now you guys know why. Hot air rises because hot air is less dense than cold air. And why is it less dense? Because it has a bigger volume, right? Temperature goes up, volume goes up. Charles' law. All right, so let's do this problem together. So a sample of gas has a volume of 2.80 liters at an unknown temperature. When the sample is submerged in ice water at 0 degrees Celsius, its volume decreases to 2.57 liters. What is its initial temperature in Kelvin and in Celsius? Okay, so let me write all this down. So let's call sample of gas that has volume of 2.80 liters. Okay, that's the first thing I see. Let's call V1 2.80 liters. Okay, and then add an unknown temperature. So we don't know what T1 is. Okay, but it says when the sample is submerged in ice water at T equals 0 degrees Celsius. Then the volume is 2.57 liters. Okay. So even before we can solve this, we should know, right? Well, it decreased. Okay. So it went from 2.8 to 2.57. That means that at 2.8, it must have had higher temperature than 0 degrees Celsius, right? But now we can calculate that as well. Okay, so let's go to the board and do that. We are still using this equation, right? V1 is equal to T1, V1 over T1 is equal to V2 over T2, right? But what are we being asked to solve for? T1, right? So we have to solve for T1 algebraically, okay? So let's multiply T1 to both sides. Then we'll have V1 is equal to V2 times T1 over T2. But we need T1 by itself, so we're going to multiply T2 to the other side. So we'll have V1 T2 is equal to V2 T1. Then T1 is equal to V1 T2 over V2. Okay, you got to practice your algebra. Okay, otherwise this part's going to be hard. Okay, so you should go through and just try to solve for different variables. All right, now we plug it in, 2.80 liters times T2. Make sure that you convert this into Celsius first. Sorry, convert Celsius into Kelvin. Always the temperature needs to be in Kelvin. Okay, for these types of problems, they need to be in Kelvin. So 273.15 Kelvin over 2.57. So T1 is going to be in Kelvin as well, right? $296 Kelvin. And we want to do like 3 sig figs. And then it wanted in Celsius too, right? So subtract 275, 24 degrees Celsius. All right. Makes sense, right? And again, how can we tell that this is a two condition problem? It gives us two things, right? Volume and temperature. Condition one, and then condition two. All right, let's go to the last simple gas law, Avogadro's law. Now, this is easy to remember. Avogadro has to do with moles, right? And so Avogadro's law has to do with volume and moles, and pressure and temperature are staying constant. Okay? Now it's really easy to figure out the relationship. This is like blowing into a balloon. As I blow into the balloon, what happens to the volume of the balloon? It gets larger. Why? Because I'm putting more moles of gas inside. So again, it's a direct relationship, right? As moles increase, so does volume. And if moles decrease, then volume decreases as well. Okay. So on the molecular level, what is happening? Well, if I'm putting more moles of gas inside a container, it's going to hit the walls of the container with a larger force. And that would mean the pressure would need to go up, right? But remember, the pressure has to stay constant. So what needs to change is that the volume needs to increase to alleviate that initial increase in pressure, okay? And so that's why the volume goes up, okay? All right, so let's look at this graph. You can see that, right? X-axis, number of moles, y-axis is volume. So you can see this upward trend, right? As number of moles increase, so does the volume, okay? And it's a linear trend as well, right? Okay, so let's now also derive the two-condition equation for Avogadro's law. Okay, so Avogadro studies moles and volume while keeping pressure and temperature constant. And we said, right, as mole goes up, volume goes up. If moles go down, volume goes down. That's a direct relationship again. Okay, so that we can say volume is related to moles directly, right? And then we can put, N over V is proportional to 1, okay? And then if we want to make an equation, N over V is equal to a constant. And it doesn't matter in what condition, right? N1 over V1 is equal to constant. N2 over V2 should also be the same constant. So then we can equate N1 over V1 is equal to N2 over V2, okay? So this is the two-condition equation, right, for Avogadro's law. All right, let's go to the slides and do an example problem. A male athlete in a kinesiology research study has a lung volume of 6.15 liter during a deep inhalation. At this volume, his lungs contain 0.254 moles of air. Okay, I'm going to write that down. So I'm going to say volume V1 is 6.15 liters. At this volume, his lungs contain 0.254 moles of air. So N1 is 0.254 moles. Okay. During exhalation, his lung volume decreases to 2.55 liters. So V2 is 2.55 liters. How many moles of gas did the athlete exhale? Okay, so we need to know how many moles are left in lungs. Right, so N2 will give us the moles left up in his lungs. And then if we subtract that from the original, then we should know how much he exhaled, right? So that's the strategy. And let's go to the board. All right, so we are looking for N2, okay? Now, even before we solve it, we can see that his lung volume went down. So that means he must have less than, right? N2 must be less than 0.254. It's going to have less, right? course, when he exhales. So we are solving for N2. That's this one right here. Okay. So to get N2 by itself, right now N2 is already on top, so that's awesome. You just have to multiply V2 to each side. So N2 is equal to N1 times V2 over 1. Okay. That's equal to 0.254 moles times V2, which is 2.55 liters, over V1, which is 6. N2 is equal to 0.105 moles. Okay, and this would be left in lungs, right? Okay. But it asks us how much did he exhale? So we have to subtract it from original. Point 149 moles exhaled. Okay, makes sense, right? Because it asks for how much was exhaled and not how much was left. Okay. Okay. So guys, that's it for this portion of the video. This was lecture 1. I'll see you guys next time for lecture 2.